Hello students, welcome to online crash course for physics in NEET and JEE. I'm going to deal with electrostatics and today's lecture is on Coulomb's force and its applications. Okay, so then we start with Coulomb's force. We already know what is meant by a Coulomb force, but let us see what exactly it actually means for it. So the Coulomb force is F is equal to K mod Q1 Q2 by R square. So upon R square, where K is equal to 1 by 4 pi epsilon naught, whose value is 9 into 10 to the power of 9 SI units. So this is a proportionality constant, and this is only for air or vacuum. Air or vacuum. Together you can call it as free space. Okay, so this is an expression for force between two point charges Q1 and Q2. Point charges separated by certain distance in air or vacuum, and the distance happened to be R. So this force is just only the magnitude. The direction is along the line joining the two charges. If it is like charges, it is going to be repulsive, and if it is unlike charges, it's going to be attractive, but both the forces are always along the line joining the two charges. Definitely. So the direction and magnitude are learned and applied separately. So the magnitude is K mod Q1 Q2 by R square, and the direction is along the line joining the two charges. The value of proportionality constant is 1 by 4 pi epsilon naught, which is equal to 9 into 10 to the power of 9 in SI units. And in electrostatics, we always use SI units because the charge has only SI unit, Coulomb. But this expression is true only for air or vacuum. Now, what is the thing for any other medium? It is actually K upon epsilon R mod Q1 Q2 by R square. So this is for any other medium. Of course, the direction is along the line joining the two charges. Here, epsilon R is a constant which depends upon the nature of the medium, whose value ranges from 1 to infinity. 1 is for air. Of course, when it is 1, it becomes the first expression, or even vacuum. Whereas infinity is for metals, all metals. So when it is infinity, the force is going to be 0. That means if two charges are separated by a metal piece, then the force happen to be equal to 0. Yeah, definitely it is going to be 0 because epsilon R is equal to 0 completely by a metal piece. Okay, so this is the expression for Coulomb's law. So this is in air and this is for any medium. Since epsilon R value is true for any medium including air, I think you can take it as the most generalized expression. So this is what it is. But what we always do it is, we always learn magnitude and direction separately. So the magnitude is given by the expression and the direction is given along the line joining the two charges. So in all the applications, we are going to learn the magnitude and as well as the direction. Okay, based on the directions, we keep adding them. Okay, that's what usually happens here. Okay, moving on to the next slide. Okay, so the magnitude of the force is equal to K mod Q1 Q2 by R square in air or vacuum. So this magnitude of force is actually proportional to the product of charges, of course mod charges. Now if I vary only the charges but not the distance or the medium, then F is proportional to Q1 Q2 modulus. So let us see some application on it. What happens if I have two charges and we combine them? The charges get redistributed. So this is all about redistribution of charges. Redistribution of charges. So let me take some two bodies here. Of course, they are identical in nature and dimensions, A and B. The first body is having a charge of 10 coulombs. The second body is having a charge of minus 20 coulombs. Identical. Identical only in the aspect of the nature and the size, but not in terms of charge. So one of them is having 10 coulombs of charge, the other one is having minus 20 coulombs of charge. Now they are separated by certain distance. Both will experience some attractive force, and the force will be towards each other because one is plus, the other one is minus, so it will be towards each other. And excuse me, and the value of that force is equal to 100 newtons. It is given. Now what we are going to do it is, if these two bodies are actually made to touch each other, they are brought in contact, then the charges will be exchanged. It will be redistributed. The charges will be exchanged because they are at different potentials. So the charges will be exchanged until both the potentials become equal. When will both the potentials become equal means when the total charge, it's only for identical, when the total charge is actually distributed equally. So what is the total charge? Q1 plus Q2, which is equal to 10 minus 20. So that should be divided equally. That means it should be made half. So you get minus 5 coulombs each. So after the recombination, the new charges on both the bodies are going to be minus 5 coulombs each. Both should have same charge. So the total charge is going to be equally distributed. Q1 plus Q2 is equally distributed. So each one gets Q1 plus Q2 by 2. This happens only in the case of identical bodies. So when two identical bodies are made into contact with each other and then brought back to the same position, the charges are actually distributed. The total charge is actually distributed equally. Now the question goes like, what is the force between them now? So the earlier force was 100 newtons. Now what is the force? So what is the thing that was changed from the first case to the second case, or before touching to after touching? It's only the charges. The distance happened to be the same. The medium happened to be the same, but only the charges are actually getting redistributed. And hence I can take F is proportional to mod Q1, Q2. So the earlier force is 100 newtons. Now the force is some F dash. The earlier charges are 10 into minus 20. Now the charges are minus 5 into minus 5. We need not bother about the charge nature because it's modulus according to Coulomb's law. So here 5 2's 5 4's. So it's going to be 8. Okay, so then F dash is equal to 100 by 8, which is approximately 12.5 newtons. I think exactly 12.5 newtons. And what is the nature of the charge? I mean, nature of the force. The nature of the force should definitely be repulsive because they are like charges. So the point here is, whenever the two bodies are touching each other, the total charge is distributed equally. So whenever charges changes, then F is directly proportional to product of magnitude of charges because the distance is same. Let us take one more example. Okay, maybe there are two bodies again, A and B. The charge on A is plus 100 E, means 100 times the electronic charge. The charge on B is minus 100 E. The force between them is F. The value is not given, just F. Okay, I'm not bothered about whether they are identical or not because I'm not going to make any contact between them. But The value of the charge is 100 times the electronic charge, 1.6 into 10 to the power of minus 19. Here minus 100e. So one is having positive charge, the other one is having negative charge. Okay, but it is in terms of electrons. Now the force between them is just F. Okay, now what happens when we transfer 50 electrons? 50 electrons, it's not 50e, 50 electrons from body A to body B, transfer. So when we transfer, the charges of A and B would definitely change, but the distance is not going to change. So if the distance is not going to change and the medium is not going to change, F is proportional to mod Q1, Q2. So what are the new charges now after the electrons are being transferred? So in this case, when electrons are removed from body A, it gains positive charge and hence add positive charge to it plus 50E. So we added some positive charge which is going to be equal to 150E. Now what happens to the body B? So whenever an electrons are given to a body, it gains negative charge. So whenever electrons are removed from a body, it gains positive charge. Whenever electrons are given to a body, it gains negative charge. So removing electrons or adding electrons, the body gains charge. Of course, charging is done only by transfer of electrons. So whenever a body loses electrons, it gains positive charge. Whenever a body gains electrons, it gains negative charge. So let's add it. Minus 100E is already pre-existing there. Add some negative charge to it, minus 50E. So we are adding some negative E. So the total value becomes minus 150E. So whether it is removing electrons or whether it is adding electrons, you are basically adding some charge. Here you add positive charge and here we add negative charge because we are adding electrons and hence the body gets negative charge. Here we remove electrons and hence the body gets positive charge. Now what about the force now? The force is proportional to product of magnitude of charges. So the earlier force is F, now the force is some F dash. The earlier charges are 100E, of course modulus, and hence we need not bother about it, 100E. The other one is 150E and this one is also 150E because we don't want to bother about the minus because it's modulus. So E's get cancelled and zeros also get cancelled. So this gets something around 5 2's 10, 5 3's 15. Okay, 5 3's 15, 5 4's 20. So F dash is equal to 9F by 4. And what is the nature of the force here? One is positive, the other one is negative, and hence it's going to be attractive. Of course, that's how we decide the nature of the force, not by plus and minus. So we got as 9F by 4. That means the force got increased because numerator is bigger than the denominator. Why did the force get increased? Because the charges on each of them got increased. Earlier it is 100 and minus 100. Now it is 150 and minus 150. Here. So the force got increased. Okay, so here the force is proportional to the product of magnitude of the charges. Okay, because the distance happened to be the same. Okay, and the medium is not changed here. Okay, I guess we followed this. Now moving on to the next part. Okay, so here if force is equal to K mod Q1 Q2 by R square. Okay, force here is inversely proportional to distance square. Of course, when the distance alone is varied and the others are kept constant, then force also varies. So force is definitely inversely proportional to distance square. Let's talk about one problem on this. Consider two bodies. Both are having some charges, Q and Q. They are separated by certain distance and the distance happen to be R. They experience some force, F, along the line joining them. Okay, now the distance of separation between them is doubled. So they experience a new force, F dash, F dash. The distance is 2r. What is the relation between the new force and the previous force? So here the charges happen to be the same. The medium is not changed. Only the distance got doubled, and hence we can take force is inversely proportional to r square. So if I write F1 by F2, it should be equal to R2 by R1 whole square. F1 is F, F2 is F dash. R1 is R, R2 is 2R whole square, which is equal to 4. That means F dash is equal to F by 4. The force got reduced by 4 times. It is definitely reduced by 4 times because it is inversely proportional to R square. So the force is inversely proportional to R square when charges are kept constant and the medium is kept constant. Okay, so in this case only we double the distance and hence we got F by 4. Now what happens if we triple the distance? When we double it, it is 2 square. When we triple it, it is 3 square. When we quadruple it, it is 4 square. So that means whenever the distance is doubled, it becomes F by 4 by 4. Okay, if it is tripled, then it is the distance is tripled, 3r. Okay, then it is going to be F by 9. It is quadrupled, then it is going to be F by 16 and so on. So this we are talking about the variation of distance, and the previous one was like variation of charges. Now let's talk about the variation of medium. Okay. Now according to our expression, F is equal to K mod Q1 Q2 by R square if the two charges are separated by certain distance in air. Okay, what happens if the two charges are separated by certain distance in some medium? Maybe it's a liquid. So the expression turns out to be K by epsilon naught, which we discussed earlier, mod Q1 Q2 by R square. That epsilon naught is nothing but dielectric constant or relative permittivity. So one is K by epsilon naught, the other one is K. Now the point is, what happens if the two charges are actually separated by, certain medium, but that was like a partial medium. So this is air, but this is medium. So then in that case, what would be the force? So how do we deal with this? It's a very simple thing. We use something called equivalent distance method. Equivalent distance method. So what is that equivalent distance? It's very simple. If there are two charges, okay, Q1 and Q2, separated by some medium, then the force in that medium is equal to K by epsilon r Q1 Q2 mod upon R square. Okay, upon R square. Or let us assume the distance to be d, then upon d square. Okay, it's in a medium. Now what should be the separation between the same charges? What should be the separation between the same charges in A? D dash. What should be the separation? So that the force continue to be the same. That is our whole thing when we say equivalent. So what is equivalent? The force should be equal. So the force between charges in medium and the force between the same charges in air should be same. So the medium varies, but not the charges. Along with the medium, the distance also should vary to keep the force same. So here the force is F means here also the force is F. In order to have the same force, equivalent distance, what is the distance then? So since force was said to be same, equate it. So we get this K mod Q1 Q2 by d square epsilon r k mod q1 q2 by d prime whole square. So k is a constant, gets cancelled, and the charges are not where it get cancelled. So what is the d dash then? It is equal to, or d prime is equal to root epsilon r into d. Epsilon r, by the way, doesn't have any dimensions. Okay, so that's an equivalent distance in air, for air. So if any distance is mentioned in a medium, we write its equivalent distance in air. Okay, if any distance is mentioned in a medium, we write its equivalent distance in air, and this is the expression for equivalent distance in air. So let us use the same principle here for something like partial medium. So in the case of a partial medium, just like we discussed earlier, this is q1 and this is q2. Maybe the distance of separation between them is d. Okay, a part of this distance is actually covered with some medium, maybe some kind of a metal, or maybe some kind of a an object which is having some relative permittivity. Epsilon r is equal to something like 9. It is dimensionless, just a number, and it is having some thickness t. Okay, then what is the force between these two? As we discussed earlier, if it is air, it is k. If it is any other medium, k by epsilon r. But this is neither completely air nor completely a medium. It's partially air here and air here, and it's a partial medium here. Then which expression are we going to use it? We talked about the Coulomb's law in air and in medium, complete. But here it was like partially air and partially medium. Or else, if there are two different mediums in between them, what could happen? So this can be easily done like this. Okay, now let us take something here. Write its equivalent distance in air. Now if you look at it, already d minus distance, d minus t, is in air, is already in air. D minus t, this is d and this is t. It's all, the remaining distance is here, which is already in air. And what is the distance which is in medium? T. Now write its equivalent distance in air. What is the expression for equivalent distance in air? It is root epsilon r into t. So t is in the medium. What is its equivalent distance in the air? So that means this is going to be air, this is going to be air, and even this is also going to be air now, because we are writing its equivalent distance in air, and which is equal to root epsilon r. Epsilon r here is given as 9. That means root 9 is 3 t. Now what happens to the force between them? F is equal to k, because we are writing everything in air, mod q1 q2 upon the distance. What is the distance between these two? Yeah, it is d, but d minus t is already in air, so keep it as air itself. Keep it as air. Plus, this is in some medium t. Write its equivalent distance in air. What is its equivalent distance in air? Root epsilon r into t whole square. So this part is already in air. This part is not in air, but it's equivalent distance in air. Now substituting that epsilon r, we end up saying k q1 q2 upon d minus t plus 3t whole square. That's it. So this is the expression, equivalent distance. That means if something is in air, we write its equivalent distance in air, which is nothing but the same. If something is in medium, then we write its equivalent distance in air by taking it as root epsilon r into t. So if it is already in air, its equivalent distance is the same thing. Okay, if it is in medium, its equivalent distance is this, root epsilon r, suffix r, relative permittivity, into t. Okay, that's an expression. Okay, I hope so you understood that. Okay. Now, moving on to the next part, the medium is changed. Okay. Now, moving on to the next part. Okay, we discussed about the medium. Now let us discuss about something else now. Superposition of forces. Now, superposition of forces will come because of combinations. So it's all about combination of charges. Combination of charges. So what is this combination of charges? You can have linear combination, you can have planar combination, you can also have three-dimensional combination. So that means the charges are distributed linearly, the charges are distributed planarly, the charges are distributed three-dimensionally. Okay, let us take one of the example. Say for example, there is an x-axis here, the linear distribution. Let us take some charges here. At x is equal to 1, at x is equal to 2, at x is equal to 4, at x is equal to 8, and so on up to infinity. Some same charges are taken whose value is equal to 1 microcoulomb. They are separated by certain distance of 1 meter, 2 meters, 4 meters, 8 meters from origin. So this is all along x-axis. Y-axis we don't have anything because it's all linear. At the origin, let us consider one charge placed here, which is Q0, which is just equal to 1 coulomb. Find force on Q0. Now, who exerts force on Q0? Each and every charge is going to exert force on Q0. Each and every charge. So, this is going to repel it by a force of F1. This is going to repel it by a force of F2. This is going to repel it by a force of F3. So all are going to repel it because they are all like charges. And we are calculating the force only on the charge which is present at the origin. So what is the force then? The force is nothing but the combination of all of them, and it is just a simple normal addition because they are all in the same directions. What is the expression for F1? K, the force between these two, mod Q Q0 upon distance square, which is 1 square. What is the F2 then between this and this? K mod Q Q0 upon the distance happen to be 2. So 2 square. Now F3, the force between this and this, K mod Q Q0 upon the distance here, which is 4 square. Now, upon this and this, K mod Q Q0 upon 8 square, and so on up to infinite. Let us take these things common in the numerator. K value is 9 into 10 to the power of 9. Q value is 1 microcoulomb, 10 to the power of minus 6. Q0 is just equal to 1 coulomb. So that's all in the numerator. And what about in the denominator? 1 plus 1 by 4 plus 1 by 16 plus 1 by 64 plus, and so on. Now this is sum of series in GP, geometric progression. What is the sum of infinite terms in geometric progression? So it is equal to A by 1 minus common ratio. What is the common ratio? It's 1 by 4. So on that, 36 into 10 to the power of 3 by 3. 12 into 10 to the power of 3 newtons. That's a total force acting on the charge which is placed at the origin. And who repels it? Every other charge is going to repel it. And since they are all like charges, they are all going to repel it, and all in one direction. Since they are all in the same direction, it is going to be just a normal addition, a scalar addition. Okay, and we add them. And these are infinite. Sum of infinite series in GP is nothing but A by 1 minus R. A by 1 minus R. A is nothing but the first term, which is equal to 1. R is nothing but the ratio, which is nothing but 1 by 4. So we get this one. So this is combination of charges and thereby combining the forces. So we have combination of forces. Of course, they are all Coulomb's force only. So the one charge is going to experience several forces here, and all those forces are acting upon that. Okay, so that's about the linear combination of charges. Now moving on to the next one, planar combination. Okay, here let us take one triangle. It's just a normal triangle. We have three charges on it. One of them is at this vertex, the other one is at this vertex, and this. So there are 3 point charges placed at the vertices of a triangle of side A, and it's an equilateral triangle. What is the force experienced by any one of the charge? Maybe this one. Okay, so this is going to experience some repulsive force because of the upper charge along the line joining them, which is equal to kq square upon distance square is a square. This is also going to repel this charge like this, which is equal to kq square upon a square. Now we need to add these two forces which this charge is going to experience. Earlier in the case of linear, since they are all in the same direction, we did a simple normal addition, which is nothing but scalar addition. But here these two charges are actually, these two forces are actually not in the same direction, not even in the opposite direction. If they are so, you can have subtracted. But they are at different angle, and this angle is definitely going to be 60 degrees because it's an equilateral triangle. So what is the net force acting on this? The net force would definitely be somewhere in between. Not just somewhere in between. It could definitely be exactly at the center. That is 30 degrees because both of them are equal forces. And hence the resultant force would be exactly in between. And what is the net force? The net force is given by the parallelogram law, which is f square plus 2f square into cos 60, which is 1 by 2, which is going to be root 3f, and f happen to be the force between the two charges, kq square by a square. So that's a net force. Now what happens for the same thing, if one of the charge happen to be minus q, the other one happen to be plus q, and this is our charge here. So there are three charges. One of them is minus q, the other one is plus q, this is plus q. Put them as A, B, C as a vertex. What is the force experienced by the charge which is placed at C? Now the charge is going to experience two kinds of forces. One is repulsive, which is going to be this way. The other one is attractive, which is going to be this way. Yes, they are of the same magnitude, kq square by a square, because the distance happen to be the same. And the magnitude of the charges are also the same, but one is plus, the other one is minus. Okay, but the magnitude is the same. And hence, the magnitude of the force is same. But how do we add these two? By taking the angle between them. Now the angle between them is no longer 60, the angle is this, which is equal to 120. You should see that these two forces are co-initial and take the angle between them. Now write the net force, which is equal to root over f square plus 2f square according to the parallelogram law, cos 120. Cos 120 is minus 1 by 2. So this 2 and 2 gets cancelled. This is minus f square, on that and this gets cancelled, and finally only this is left, which is f. Root f square is f, which is equal to kq square by a square. That's a net force. And what is the direction of this net force? The direction of this net force is going to be exactly in between, making some angle 60 degrees here, bisecting angle. So that's a planar combination of forces. That means the charges are distributed on a plane. And let us take one more example for this. Say for example, there is a square. And at the vertices, we have some 4 charges which are of identical value. Okay. Now what is the force experienced by any one of the charge on the vertex? So each other charge is going to exert one force. There will be totally three forces because there are three other charges here. So the three charges are going to exert three forces on it. So the first charge is going to repel it like this, kq square by a square. This charge is also going to repel it like this, F is equal to kq square by a square, because the distance happen to be the same and the magnitude is also the same. Now what is the resultant force according to the parallelogram law when the angle is 90 degrees? The resultant force is going to be equal to root 2f, and this force and this force are added, the resultant force is going to be root 2f, and that is going to exactly be in between 45 degrees. Okay, so we added this force, these forces, and we got root 2f, okay, from parallelogram law. Now what about the third charge, which is diagonally opposite? That's also going to repel it, okay, with a new force f dash. But before we write the value, we should know the distance here. So here it looks like a right angle triangle. So this is A, and hence this is root 2a from the Pythagoras theorem, which is equal to the length of the diagonal. So what's a new force then? K, Q into Q, Q square upon distance square, 2a square. So this force and this force differs, and hence call it as F prime. But this root 2f and this f dash are in the same direction, and hence we can simply add them by scalar method. So root 2f means kq square by a square, f prime is kq square by 2a square. So kq square by a square taking common, you get root 2 plus 1 by 2. That's what we get it. Now what happens? This is the net force. Okay, so this is the thing. What happens if this charge happen to be negative? Only that, diagonally opposite. So this will be attractive rather than repulsive. And how is this root 2f and this f dash then? Opposite in direction. So what is the net force if they are in opposite in direction? It would have been kq square by a square into root 2 minus 1 by 2. That's the net force if it is minus diagonally opposite. Okay, that's a combination of charges and thereby combining the forces on a planar distribution. Now let us take three-dimensional distribution. So 3D distribution. Let us consider some four charges which are placed at the four vertices of a square. Still, it is a planar distribution and it is a square, perfect square. Now, let us consider one more charge here which is placed at certain height from the center. So joining all of them would actually mean it forms like a pyramid. So at this apex, keep one more identical charge. So totally there are 5 charges placed at the vertices and at this apex of a three-dimensional figure. It looks like a pyramid. Okay, now what is the force experienced by this charge which is placed at the top? Okay, so let us take some 2 charges first. One of them is this, the other one is this. Okay, the direction of force will be along the line joining them, which is F, which is equal to K Q square upon distance square. Now we need to get the distance that is between these two. But how do we get this? By drawing one right angle triangle here. So how does the triangle look like? Let me draw it once again. It looks like this. Okay, so that is how a right angle triangle looks like, where the base of this triangle is on the square and rest are all out of that square in a plane which is not belonging to the square. So we all know this distance is nothing but half of the diagonal, which is a by root 2. This is height of the pyramid. Then according to the Pythagoras theorem, this is going to be root over h square plus a square by 2. So the same thing we carry here, which is equal to h square plus a square by 2. Okay, but the root and the square gets cancelled in the form of coulombs. But that's the direction of the force. Now, if I just take this angle as theta, that means this angle is theta, I can resolve this force into two components. So this is f cos theta and this is f sin theta. You can see that. One is f cos theta, the other one is f sin theta. Okay. Now, if you take another charge which is diagonally opposite to it, then it also gives us the same force. On resolving the same force here, the same angle here, theta, just like this. So you get here as f cos theta and here it will be f sin theta. So this f cos theta and this f cos theta will cancel out each other, which are for the diagonally opposite charges. Similarly for these two. And hence only f sin theta keeps adding them in the same direction. And hence what is the net force at that particular point? The net force is equal to, so this will have 1 f sin theta, this will have 1 f sin theta, f sin theta, f sin theta. So 4f sin theta. If it is 4f sin theta, what's the expression for f? This is the expression for f. K q square by h square plus a square by 2. And sin theta is nothing but opposite side by hypotenuse. That means h upon h square plus a square by 2 under root. Now, on simplification, 4k q square h upon h square plus a square by 2 whole to the power of 1 plus 1 by 2 is 3 by 2. That's a net force. That's a net force acting on the body. So here the three-dimensional distribution should be viewed by resolving the forces, or we can use in the vector form. So what charges we have taken initially is that the diagonally opposite. They produce forces in this direction, which has a component like that, f cos theta, which gets cancelled. That means the force components which are along the plane gets cancelled and the perpendicular to the plane gets added up, and the net is going to be 4f sin theta because of the 4 charges here on this charge. So 4 is 4, kf is this, and sin theta is something which you can get it from this triangle. So that's how we get the total force on a three-dimensional distribution. Okay. Now, other than the charges which exerts force on each other by using an expression called Coulomb's force, there could be some other force here. Maybe a gravitational force, maybe a frictional force, or maybe some other tension force. What happens if all these forces are there? Then we have to use NLM. NLM, Newton's laws of motion. In Newton's laws of motion, if the charges are in equilibrium, the total force is equal to 0, including everything, including Coulomb's force and everything. If it is not in equilibrium, the total force is equal to mass into acceleration, according to Newton's second law. So, if you have more than one force, if you have more than one force, okay, I mean to say other than Coulomb's force, then we have to use Newton's laws of motion. Write all the forces and equate to 0 if it is in equilibrium. Write all the forces and equate to m into a if it is not in equilibrium. So let us take one of the example for it. Okay, so here we have something like a pendulum. Okay, so there are charges given to the identical pendulums having same length, same mass, and same charges are given. If these two pendulums are not having any charges, they would have been hanging from the same point at the same end here. But since the charges are given, they get repelled. Maybe they get repelled to certain angle theta here with the vertical and certain linear distance of separation r. But why would they stop after repelling to certain distance? Because the Coulomb's force is going to repel them away. This is how the Coulomb's force is going to be along the line joining them, which is going to be equal. F is equal to kq square by r square on both of them, action reaction. The Coulomb's force is an action reaction pair. Both the charges would be experiencing the same force. F is equal to kq square by r square. Now, if they are going to experience force because of the charges, they should be separated like that. And they should go up to this maximum separation, which is going to be infinite. Which is going to be 180 degrees separation. Okay, so that's not happening here. They are actually going to certain distance and then stopping. If it is stopped, then some other force should be existing there, other than the Coulomb's force. So let us write all the other forces here. One of the forces is gravitational force, which is going to be the same on both the bodies because they are identical. The other force is also going to be tension, which is also the same on both of them. Now, since it is at rest, we can balance the forces. How do we balance the forces? Is by resolving the tension. If this is theta, then this is also theta. Resolve the tension. This is going to be T cos theta, and this is going to be T sin theta. Now, T cos theta and mg must be balanced. So let us balance it. The first point is T cos theta is equal to mg. The second is T sin theta and this Coulomb's force must be balanced. T sin theta is balanced with the Coulomb's force. Now divide them 2 upon 1. So when we divide them, T gets cancelled. Sin by cos is tan, which is equal to kq square by r square mg. That's a theta. Or theta is equal to tan inverse kq square by r square into mg. So that's a theta separation here, and the angular separation between these two is equal to 2 theta. Okay, tan inverse this. That's an angular separation. In fact, the angular separation is nothing but 2 theta, but not theta. Okay, but what is the linear separation? It is r. So can we use and find that? Yeah. Now what is r? What is theta? Tan theta from this triangle. So this distance happened to be r by 2. This distance, according to the Pythagoras theorem, it's going to be L square minus r square by 4. And from this, tan theta can be written as opposite side, that is r by 2, by adjacent side, which is root over L square minus r square by 4. Okay, which is equal to kq square by r square mg. This is tan theta. Now we need r, but this r equation is a bit complex. Here we have r square and then r square. And this r square is inside the root and the 2 along with some L square. So I think the simplification is going to be a bit longer and it's going to be a bit difficult. So let us take one approximation. So what happens if it is a long pendulum? If it is a long pendulum, L is going to be very much greater than R, and hence this term can be ignored. Then we have only L in the denominator. So along with 2, then we have kq square by r square into mg. R square and r on multiplying, we get as r cube, which is equal to kq square by mg into 2l. And if we want r, let us take cube root, which is equal to kq square 2l by mg whole power 1 by 3, which is the cube root. So that's a linear separation. Of course, that's only for an approximation. And this is an angular separation. Of course, in fact, the angular separation is 2 theta, not theta. Okay, so by this expression, we can get angular separation, and by this expression, we get the linear separation between the two pendulums. So the two pendulums are actually given some charge q here, and these two charges are going to repel it, and they are going to go by certain distance and stop, because the t sine theta is balanced by this repulsive force and t cos theta is balanced by mg. This is what we got the expression. Okay, so this is a tan theta is equal to this and r is equal to this. Okay. Now, continuing with the same pendulum problem, okay, where the pendulums are separated by 2 theta, and the angle is given by tan theta is equal to kq square by r square mg, where k is nothing but 1 by 4 pi epsilon naught, as well as the linear separation, which is approximate value, which is equal to kq square 2l by mg whole power 1 by 3. Now let's see different cases, what exactly these values are going to differ upon on what factors. Say for example, if both the bodies A and B are not having same charges. Earlier we took same charges. Now what happens if they don't have same charges? Is this going to vary? Yeah, it is going to vary. Okay, then tan theta is going to be equal to k q1 q2 by r square mg. Yeah, that's it. Now, is the theta going to be same for both of them? In fact, yes. Now, how is theta going to be same even though the charges differ? It's all because when charges differ, the electrostatic force on both of them still continues to be the same. So earlier the force was kq square by r square. Now the force is kq1 q2 by r square. Whether it is kq1 q2 by r square or kq square by r square, the force on both of them should be the same according to the Newton's third law. So if the force is same, mg is also same because masses are equal, then tensions are also same and angles also will remain the same. So which you can actually understand from this. So theta 1 is equal to theta 2. Okay, so even though when the charges actually differ. Okay, now what happens if that is submerged in some liquid? Submerged in liquid. Submerged in liquid. Yeah, whenever the pendulums are submerged in a liquid, obviously something should change. So let's see what it's going to change. Yeah, the force is going to change. Instead of k q1 q2 by r square or kq square by r square, let us take the charges as identical. Kq square by r square, we have k upon epsilon r q square by r square, where epsilon r is dielectric constant. Okay, so this is theta and theta. Now what the case is, if the angle is same in liquid and air, then what is the condition? So since angle is said to be same, so let us equate the angle in air and angle in liquid and see what the condition is. So what is the expression for angle in air? K q square by r square mg. That's what we learned in the previous case. What is the expression for angle in liquid? That was given as a condition. Okay, it is like instead of k we have k by epsilon r because the medium got changed. The charges will not change, so q square by r square. The distance also is not going to change because theta was said to be same. Then what about mg? Now mg would change. Mg in air is mg, but mg in a liquid is According to the equation, it is mg into 1 minus density of liquid by density of body, that is density of the bob. So this mg has changed. The mg inside a liquid is different. Okay, now let's cancel them. So when we cancel it, we get 1 by epsilon r is equal to 1 minus density of liquid by density of body. That's a condition. In order to have same theta even when it is submerged in a liquid. So when it is submerged in a liquid, not only electric force changes, but the gravitational force mg also changes because there is a Bion force. And from buoyancy, this is the expression for weight of the body in air, in liquid. Density of liquid by density of body. Rho L by rho B. Body is nothing but the bob of the pendulum. Okay, that's a condition. You can use the condition directly. So similarly, let's go with another case, case 3. What happens if you take it in space where there is no gravity? And the two pendulums will be separated by maximum separation. Okay, and they will experience some force. Of course, it is electrostatic repulsive force, which is balanced by the tensions. What is the tension inside that? Which is equal to F, which is equal to K Q square upon what is the distance between them is 2L whole square. That's how you get the tension. The electrostatic repulsive force is same on both of them, and it is balanced by the tension inside the rho. And what is the maximum angular separation between here? 180 degrees. Because there is no gravity to pull it down, and hence they will be separated to a maximum distance of separation. Okay, so that's what we get it. So we took the same expressions and tried to see what happens if the charges are different. Charges are different, but the forces on both of them will be the same according to Newton's third law, and hence the angles would remain the same. Here, what happens if I submerge inside the liquid and the theta is to be same? That is given as a condition. That we are taking the condition that theta should be same. In that case, what should be the requirement so that theta would be same? So I equated the value of theta in